Good morning and welcome to Tech 293 for Thursday, January 14th. If you're watching this, then I'm glad you're back with me today and I didn't scare you off on Tuesday. A couple of reminders before we get started today. First of all, let me know if you have any questions about what we talked about on Tuesday. Anything regarding the schedule or the format of the class or how this class is going to go. May as well ask the question now, and we'll get it straightened out. The second thing to remind you of is that we have the first quiz, and it's a very straightforward. It's an easy quiz. Don't be stressed out about it at all. But don't forget about it. It's due on Sunday, January 17th. That's this Sunday by 11:55 p.m. So you can do it now. There's no reason to wait until Sunday to do it. It's mainly about the course materials that we talked about on Tuesday. So it's an easy quiz. It's easy points, so don't give away those points by forgetting to do the quiz. Make sure you do that by Sunday night at 11:55 p.m. What we're going to do today is I think I'm going to make two videos today. The first video is going to be an overview of materials testing. So basically what we're going to do is we're going to talk about in just a little bit of detail about each of the types of tests that we're going to do in this class. And then there's a couple more that I want to talk about that we're not going to talk about in detail in this class, but they're important, so I'm going to mention them anyway. So if you don't fully understand everything that I say today in these in this overview of materials testing, that's probably okay. We're going to talk about pretty much every one of these things in a lot more detail in the coming weeks and months. I really just want to give you a high-level overview of these things so that when we talk about them in more detail in the coming weeks and months, it'll jog your memory and you'll say, oh yeah, I know we kind of talked about that and that kind of made sense at the time. And now that I have some more context, I understand it a little better and in more detail. So that's the goal of today, is to give you a little bit of information about a lot of different things. That's what we're going to do today in the first video. All right. In the second video today, we're going to talk through the instructions for Lab 1. And we're going to do this every single time for all of the labs. On one day, we'll discuss the lab and talk through the instructions. And on the next day, we'll actually do the lab. That way, you should know what you're doing when you actually are doing the lab, when you come into Turner Hall and actually are in person doing the labs. But we'll do the same thing for Lab 1 and Lab 2 also. So in the second video today, I'm going to talk through the instructions for Lab 1 and what we're going to do next Tuesday for Lab 1. And I've said this before, but for Lab 1, it's not going to be in person. It's going to be a video just like this is. And I'm going to be doing Lab 1, so I'm going to be calling out the measurements and the data, and you'll be writing down the data, just like you were actually here doing Lab 1 and pretending like I'm your lab partner for Lab 1. All right, so that's what we're going to do in the second video today. But let's go ahead and get started with the first section, which is the overview of materials testing. So to do that, I'm going to share my slides. All right. So just a couple examples to get us started. You might see the picture on the screen. So that is an Arleigh Burke class destroyer undergoing shock testing, which is a type of materials testing. And this is the lead ship of the class. So this is the USS Arleigh Burke undergoing shock testing during sea trials, the first time it actually went out to sea. And they do this with the lead ship, the first ship, in each class, each new class of ship. And it's to make sure that the ship can withstand some amount of battle damage, in this case due to a mine going off nearby. And just to make sure that it's seaworthy, you know, and not only that, but battle-worthy, I guess. And I think this is kind of fascinating. They do this, and it reminds me of an internship that I had when I was an undergrad. I spent one summer out in the Washington, D.C. area at a Office of Naval Research lab, where my job was on the propeller design. I was an intern basically for a group that designed propellers for Navy ships, which was pretty awesome. It was awesome, but then again, a lot of that stuff is confidential, and at the time, I didn't have a security clearance. I did later when I was in the Navy, but that was before I was in the Navy. And so I didn't get to see some of the really, really cool stuff, but I saw some pretty cool stuff nevertheless. Propeller design is pretty cool, and that whole lab was pretty awesome. Anyway, the point I want to get at is the building next to ours is where they did simulated shock trials. Well, I shouldn't say I should say model. They did model shock trials. So what they would do is they would make models of ships, and then they had a pond. They were remote control ships, and they would have these ships, and they would be in the pond, and they would set off explosions next to these model ships. And so they did that as they were designing the next classes of ships to test out its battle worthiness. And so every once in a while, I just remember from that internship, every once in a while, not every day, but once a week or something, when they do tests, every once in a while you hear just a boom from the building. I mean the pond next to the building next door, which was pretty wild, just kind of crazy that every once in a while you just hear an explosion, and that was normal. So that was I thought pretty cool. And so that's one example of kind of dramatic materials testing. Here's one that's not quite as dramatic. I've got what looks like a big old bolt. It's not a bolt, it's actually a stud because it's threaded on both ends. But this is a pitch stud from a GE wind turbine. I think I mentioned last time that I used to work for GE, General Electric, specifically managing some wind farms around here. So it's not supposed to do this. It's not supposed to come apart in two pieces like this. This is the part, one of many, probably about 50 pitch studs that go around the perimeter of the base of the blade and hold the blade onto the hub. And the hub is what rotates around. So the hub is what all three blades are attached to, bolted to. So one side of this, actually this side of this, screws into a threaded hole in the hub, and then the blade gets set on top of this, and then a big nut goes down on top of this, and then it gets torqued to a really high value. I don't remember. I have it somewhere, but the torque spec on this, but it's a very high torque spec. Well, we were doing some maintenance one time on a wind turbine, and actually, this is not actually that unusual. It happens. But we were torquing down, checking the torque on a bunch of the pitch studs, and we heard sort of an explosion. It's really loud when this happens, as you'll see when we do tensile testing. But this is even larger than the specimens we're going to do tensile testing on. But that's basically what we did. This is basically a tensile test where we were torquing down the nut, which put this in tension, and whether it was due to substandard quality of steel or an inclusion some here in the steel, we don't exactly know, but it broke. And like I said, it's not that unusual. In fact, there are, like I said, about 50 of these going around the perimeter of the blade, so we can actually operate the wind turbine still, even if we're missing one of these. If we're missing more than one of these, then you're not allowed to operate the wind turbine anymore, just for safety measures. But when one of these breaks, it's not supposed to, and so we had to send this. We had to send this back for some testing. Or you know what? Maybe I'm trying to. It was probably 10 years ago, so I'm trying to remember exactly what we did. I'm trying to remember if we sent this one in for testing and they sent it back to me. Or I'm trying to remember if we had more than one break and we only sent one in. Honestly, I don't remember, but I do remember that we had a few break on the wind farm, and we sent them in for materials testing, just because they're not supposed to do that. And so in the GE lab, then they analyzed those specimens and determined whether they met the required specs that they were supposed to. And once it got beyond that, then that was not in my realm anymore. I was on operations. My job was to operate the wind turbines, not to deal with the material specifications. That was not part of my job at that point. But anyway, that's another example of when you might want to do materials testing. So there are a couple of real life examples. So who and what, when, where, and why you might want to do materials testing. Well, who's going to do the materials testing? A bunch of people could possibly do the materials testing. The supplier itself, let's say the supplier of these bolts, whatever company, I couldn't even tell you what company is making these pitch studs or anything, but whatever company is making those is probably testing some sample of their product in-house because they want to make sure that they're selling a quality product. If they don't, then they're going to go out of business because nobody's going to buy their product. So the supplier is going to do some testing. The user, that would be, in the example would be GE. GE is probably doing some testing as well to make sure that the material they buy is meeting their specs. And then also a third party. So this would be neither the supplier nor the user, but they might agree to send the product to an impartial third party test facility. That way it's impartial and there's no accusations of doing the test incorrectly to skew the results one way or the other. So oftentimes either the supplier or the user will send the material to a third party test lab. There are a number of these throughout the country, and they will do the testing themselves. What do you want to test? There are different kinds of properties that we'll discuss in a minute, and we're going to categorize the properties, the material properties, as either intrinsic to the material or extrinsic to the material. And we'll talk more about it in just a second, but it's probably easier in many cases to measure extrinsic properties, but usually we are more interested in intrinsic properties. I'll save that discussion for just a couple of minutes from now. When do you want to do it? Well, you want to do some testing before production because you don't want to put bad product into your final assembled product, but you're also probably going to keep doing testing after production and as you're doing the production as well. Where do you do the testing? You're going to do it in labs, test labs that could be provided by the supplier or the user of the product, or in, like I said, third-party quality assurance labs. And the procedures are standardized. That way it's not somebody that's being like, let's see, I think I'm just going to take this and, I'll just stretch it apart, applying another 1,000 pounds per second or something like that. Or you don't want people doing the testing that are just kind of making up the test protocol as they go, because then you would end up with wildly different results depending on who's doing the testing and how they're doing the testing. So there are painfully specific protocols for testing that are listed in ASTM, American, I have to look that up. American Standards for Testing the Materials. I believe that's the acronym. No one ever says it out. Everyone just says ASTM. So ASTM procedures are the standards by which everyone performs the tests. They're kind of painful to read. Most of the ASTM documents for testing are, I would say between 12 and 20, 25 pages, something like that, in pretty small print. And they are kind of exhaustive in their description of what the test procedure needs to be. But that way it's standard, no matter who is doing the testing, you should come out with pretty much the same results. All right, and that's what we try to go by in this class. I try to write the labs such that they go by the ASTM procedures. So some of the things in the labs later on in this class might seem kind of arbitrary, but most of the time they're not. Most of the time we're doing it that way because that's what it says in the ASTM procedure. Why do you do it? You might be designing with a new material. Let's say I've got a certain grade of steel right here, and obviously it broke, so I want to design with a different grade of steel. And I would design the new product with with the knowledge of what, say, the elastic modulus is of that new type of steel. So I can look all that up online, and if I know 1040 steel wasn't strong enough, I can go and I can look up the properties of 1080 steel, and using the known properties of 1080 steel, I can design a new part just by knowing the standard intrinsic properties of the material. All right. Also, why do you want to do testing? You're also verifying the materials and the parts that you are using currently as well. All right, who does it? Yeah, I pretty much already covered this. The suppliers of the material are going to verify what they're selling. The companies that are using the product will also have quality control labs, and they're going to verify what's coming in from the suppliers to make sure they are using quality products in the parts that they are manufacturing. And then also sometimes independent testing labs are used as well, just because they're impartial. Why do you test the materials? Oh, I kind of covered this already also. So when you're designing a part, usually you have the material that you're going to make that part from in mind. So you can look that up, and you already know, even before the part is finished, you know what the strength characteristics are going to be. And you need to do that in order to design the part, because otherwise you don't know whether to make that pitch stud 1 inch in diameter or 1.5 inches in diameter. That's all based on the strength calculations based on the known properties of the materials. You also want to verify that you're using good quality stock in your production and making sure that the products that you're making are going to meet the specifications for your customers. All right, here are some properties that can be tested. This is certainly not an exhaustive list, but we can divide the tests that we do into a bunch of different classes. Like we can test for physical properties and mechanical properties, thermal, chemical, electrical, optical properties. We don't have time for all of these tests in 293. In 293, we emphasize mechanical properties of materials, hence the name of the course. And so we are going to do tests for strength and stiffness and ductility and hardness and impact strength as well, or impact toughness, actually. We're also going to talk about density, and we're going to do dimensions as well. So those are physical properties of materials. The others, thermochemical, electrical, optical properties, most of the time those are a little bit more difficult to measure, and for general purpose use, they might not be as relevant to most applications. There definitely are applications where conductivity is worth knowing. If you're designing anything that's going to be an electrical component, you probably want to know its conductivity. Sometimes you got to be careful about that. You wouldn't want to make a circuit board out of something that is highly conductive, or else you're going to sort out everything else on the circuit board, for example. Yeah, the ones in bold are the ones that we're going to focus on in TEC 293. We can further categorize the materials as either being intrinsic, we can categorize the properties as either being intrinsic properties or extrinsic properties. And here I think is the best way to state the difference between an intrinsic and an extrinsic property. If you are talking about an extrinsic property, then it depends on how much of the stuff you have. Some examples that we list on here, like mass and weight, size, dimensions. If I have a little bit of steel, it's going to have different dimensions and different mass than if I have a big hunk of steel. So dimensions, mass, size, weight, all of those are extrinsic properties because it matters on how much of the stuff you have, or the shape that the stuff is in. It matters what shape the stuff is in. Is it in an I-beam or is it in a channel beam, something like that? It would matter for an extrinsic property. For an intrinsic property, it shouldn't matter. It doesn't matter what shape the material is in. It doesn't matter how much of the stuff you have. I should be able to do a test on the strength of the material. And if we're getting to an intrinsic property, which strength should be, then it doesn't matter how much of the stuff I test, which is convenient because that way we don't have to test full size, I-beams that would be used in the Willis Tower. We can test on much smaller scales. I can test, well, here's a good example. I was going to show this later anyway, but here's one of the specimens that we're going to test. This is steel, and this is one that was tested, I don't know, some semester earlier, and obviously we broke it. And obviously this is a much smaller specimen, smaller in diameter than this would be. But the convenient thing is that I don't have to do a test on this necessarily. I can do a test with a smaller specimen, and then I can scale things up, and I can know exactly what the mechanical properties of a larger specimen should be. And that's because when we're doing the testing, we want to get to intrinsic properties of the material. All right. So intrinsic doesn't matter how much of the stuff. Here's another pretty good clue. If you can look it up in a data table online, which you're going to do quite a bit of in this class, it's probably an intrinsic property. Probably. There are standard size I-beams that are probably also in tables that you can look up for dimensions of standard I-beams. You can probably look up online. And the dimensions, as we've said, are an extrinsic property, not an intrinsic property. But most of the time, for most things, density and rigidity and hardness and strength, for those types of things, those are all intrinsic properties. You can look them up, and you will, in a table online. So density, hardness, thermal and electrical conductivity, elastic modulus, which is the same thing as modulus of elasticity. Those are intrinsic properties. All right, a few terms that you're going to hear repeatedly in this course. So I want to go ahead and introduce them now. The first one is the strength of a material. So here's a definition of strength. And it is a material's ability to withstand a load. So let's say, here's a specimen. Here's a plastic specimen. So if let's say I'm doing a tensile test, because this is a tensile test specimen. So if I pull on this and try to stretch it out, even if I deform this, and I will if I pull hard enough, even if I cause this to deform, the maximum force, and we'll have a better definition later, but it's its ability to withstand that force or withstand the load without breaking, even though it's going to deform and stretch as it does so. All right, so you should know that first bullet point, what the definition of strength is. And there's different kinds of strength, and we will talk about tensile strength and compressive strength and flexure, that's when I bend it like this, and shear. We don't do shear on something like this, but if I was to, pull on this side and push on that side and try to get it to slide against itself, that would be shear. That's strength. Stiffness or rigidity, they're synonymous. They mean the same thing. And we're going to measure it by something called the elastic modulus or the modulus of elasticity, or you'll also hear Young's modulus. We'll talk about that later. They all mean the same thing. And it's actually analogous to, don't worry, we'll talk about this more as well, but the reason we do lab 2 has to do with springs, and it's actually analogous to the spring constant, how much force you have to apply to a spring to get it to deform by a certain amount. There's a very intimate connection between a spring constant and the modulus of elasticity of any other material. So we'll talk more about that connection later on. But basically, stiffness or rigidity is the material's ability to resist changing shape. All right, so that's the big difference between stiffness or rigidity, and strength. In strength, I don't care if it changes shape or deforms. I just want to know what's the overall, how much load can it break, even allowing for deformation. With stiffness or rigidity, I want to know its ability to resist changing shape. Its ability to resist changing shape, like this. This would be flexural rigidity. Okay. So make sure you are clear on that. It is not the same thing as strength. In lab reports, sometimes I see students use these terms in the wrong way. When they mean strength, they put in stiffness or rigidity or vice versa. So make sure you're paying attention to that. All right. I think I kind of mentioned this already, but we can measure stiffness in compression and in tension and in flexure and in shear. Hardness is yet another term. Hardness is not the same thing as strength, and hardness is not the same thing as stiffness or rigidity. What hardness means, what it means is the resistance to scratching or indentation. So, let's take this plastic first of all. So it's a piece of plastic. It's, I don't even know. It's not labeled, so I have no idea even what kind of plastic this is. But maybe if I push really hard with my fingernail, maybe I could leave a little indentation. I think I probably could. It's not that hard. Or I'm sure that if I took my key, my car key, I could scratch it, and I'm sure I could leave an indentation on it. So it's medium hardness, I would say. Now imagine this specimen is made out of steel, pretty much any kind of steel. If I took my car keys, I would have a much more difficult time. I might still be able to make a scratch. I probably could, but probably not as deep of a scratch as I can with this plastic material. So the resistance to scratching or say indentation with your fingernail, that's a good qualitative test to determine how hard a material is. And there are differences between different kinds of metals and different kinds of plastics. We use different scales for different materials. We'll get into all of that. And much later in the semester, we'll even talk about how you can actually take the same piece of steel, this steel right here, and I can actually adjust different properties, including its hardness, but other strength properties as well, and ductility properties, by heat treatment. I can throw this in the oven and let it bake for a while. I'm using that term kind of loosely. We don't call it baking, obviously, but we can heat treat it. And if we're careful about how long we treat it and for what temperature, then we can control the properties, including hardness and others, by heat treatment of those metals. Not just steel, but metals, most metals we can heat treat. All right, here is an overview of some of the tests that we will do in TEC 293, and there are a couple at the end that I wanted to include because they're important, even though we don't have time to do them in TEC 293. So the first one is going to be Lab 3, and that's hardness testing. You're going to do this, and this is the first in-person lab in the class. So the plan is for everyone's going to come in small groups while maintaining social distancing. We're going to do this hardness testing with a Rockwell automatic hardness tester. It is super easy. It's basically it's a little bit more complicated, but basically I'm not exaggerating too much when I say you push the green start button and you wait for it to spit out a number like you see up here. You see it says 61.8 HRC. That means it has a Rockwell C scale hardness of 61.8. So we'll talk more about that in a couple of weeks. And we'll talk about how it does it as well, like the steps that it's doing, even though it doesn't tell you what it's doing, because the Rockwell automatic tester is it makes it almost too easy. But we will talk about what it is that machine is doing. Then we'll get into labs 4 and 5. Well, 4 and 5 are tensile testing, and lab 6 is compressive testing, which is really almost the same as tensile testing, just in reverse. We're squishing it instead of pulling it apart. Tensile means tension test, which means you're stretching it, you're pulling it apart, you're trying to pull it apart. One important thing that I want to, well, we'll get to this in a second, but let me first talk about the parts of the machine. And this is a smaller version of the machine that we have in the plastics lab, Turner 122, I think it is. It says plastics lab over the door from the hallway, so you'll see it. What we've got here is a universal test machine, UTM, and we have a base down here, otherwise known as a fixed crosshead. So it goes across the machine and it's fixed. This part is not moving. What's moving is this part right here is just slowly moving up, and as it moves up, it's stretching the specimen. Whatever's in there in the grips, the jaws, it's slowly pulling it apart. And these are the jaws right here and right here. And then the measurement of the force, how much force is applied, is by this gauge right here. This is called the load cell. And on our machine, it goes up to 100 kilonewtons of force. And that, if you do the math, that's about 22,000 pounds of force that our machine can apply. That's a lot. That's a lot of force. So we're lucky actually to have such a. It's a really good piece of equipment. It was. We paid about $75,000 for it, but we got an academic discount. We got about half price. So normally it's more like $150,000. So it's a nice piece of equipment. This is kind of a weird picture. It's not obvious what it's testing. What this is two pieces of Velcro, and it's doing this is a standard ASTM test, believe it or not. There are at least hundreds, I dare say thousands of standard ASTM tests. And this is one for the, like a hook and loop Velcro fastener, and it's pulling the pieces of Velcro fastener apart and measuring the amount of force that it takes to pull the Velcro strips apart. Kind of funny. All right, here's the way that testing is accomplished. We'll talk about this again because it's a little bit counterintuitive. Most people assume that the way you do tensile testing is by having a part and applying a certain force to it. It's intuitive, you know, and that's kind of how we do lab 2 also. But when it comes time for real, actual tensile testing, this is the way tensile testing is virtually always done. You don't just take a specimen and apply a force to it and see what happens, how much it stretches. Actually, it's the reverse of that. What you really do when you do tensile testing is that you hold the part in the jaws, and then you set the machine for how fast to pull it apart. So it is pulling it apart at, say, 1 inch per minute, something like that. And then as it's stretching it at a rate of 1 inch per minute, it's measuring how much force is being applied by the part, trying to hold itself together. All right, so most people assume that you apply a certain force to it and you measure the stretch, when in fact it's the opposite. The way that tensile testing is done is you apply a given stretch and you measure the amount of force that it takes to apply that stretch. All right, we'll talk more about that, but the reason that's important is because that determines which is the independent variable and which is the dependent variable. And it's important to keep those straight. Here's what ductile specimens tend to look like as you pull them apart. L sub 0 means the original length of the part. So it might look something like this. Originally, this is untested. And then as you stretch it and pull it apart, if it is a ductile material, then at some point you will start to see something called necking. Necking is a rapid localized reduction in cross-sectional area. And I have tons of specimens here, but here's one that I grabbed. So this is an example. I can't, I can't guarantee it's the exact same material as this one, but it could be. I don't know. It doesn't really matter. Here's the untested specimen. You can see it if I hold it right in front of my face. You can see it better. And then here's another specimen. You can see necking right here. So specifically, this happens after you exceed the ultimate tensile strength of the specimen, but don't worry, we'll talk more about that later. All right, these concepts are really important because we will use these throughout the entire semester. So in fact, I think what I want to do, I am going to switch over to the document cam real quick because I want to write these out. All right, so what I want to write out, these are really important because we're going to use them over and over again in this class. So the concept of stress, I'm going to write it out in words, and then I'll write it out in symbols like we're actually going to use it. So stress is equal to force divided by area, and the area I mean is the cross-sectional area. So if I take this specimen right here, I would want to measure the cross-sectional area of the test section right here. And that's the area that we're talking about. So this is a cross-sectional area. So that's in words, that's what stress is, but we're going to use symbols. And the standard symbols for these things, the standard symbol for stress is the lowercase Greek letter sigma. And if you want, I made that tail maybe a little bit longer than it needed to be. But that's, if you write it like that or like this, something like that. That's a Greek lowercase sigma. And that is the internationally recognized symbol that we use for stress. And stress is equal to force, which we just abbreviate with F, divided by A, which is area. All right. Yeah, so that is our general definition of stress. We will customize this definition a little bit when it comes to things like flexure stress or compressive stress. We'll be a little bit more specific, but in general, we're going to use this basic equation throughout the entire course. I mean, even through Lab 9. In Lab 9, you're going to use this calculation to calculate shear stress, and we'll just kind of customize it just a little bit for shear stress. So that's stress. The other concept that is really important, my camera keeps wanting to refocus. The other concept that's really important is called strain. And strain, I'll put it in words first. Strain is equal to the change in length of a specimen. I'll just write change in length divided by original length of the specimen. All right, so I'll probably never write it out in words like this again. The international symbol for strain is a lowercase Greek letter epsilon. That's an epsilon. It looks like a backwards 3, right? But that's just, I didn't come up with that. I didn't decide that was how it's going to be, but that's just the internationally recognized symbol for strain. And strain is equal to change in length. So the way we write that is delta. Delta always means change in something. Delta means change. Delta L, that's the change in length, divided by L sub naught or L sub 0. That means original length. I guess you could consider that to be an O for original length. So once again, this is a concept that we will use repeatedly over and over again in this class, and we're just going to customize it for different types of strain. We'll use this in tension, we'll use it in compression, we'll use a concept kind of like this, not identical, in flexure testing even, kind of like this. Anyway, these are really important concepts. Make sure you are very comfortable with these concepts because we're going to use them over and over again in this class. All right, switching back to units for stress. All right, so stress is force divided by area. There's basically two ways to measure force. You can measure in freedom units, imperial English units, or you can measure in metric units. We need to be comfortable in both because we live in the United States. So if you're doing work for a company in the US, there's a decent chance they're going to be using freedom units. If you do work for a company that is anywhere else, they're going to be using metric. Quite honestly, even if you work in the US, there's a pretty good chance they're going to use metric. When I was at GE, pretty much everything was in metric. Okay, so in English or freedom or imperial units, your force is going to be in pounds force, and your area is going to be in inches squared. So your stress is pounds force per inch squared, or PSI. If you're in metric, then your force is going to be in newtons, capital N, and your area is going to be in meters squared. And one newton per meter squared is a Pascal. So your units for stress in metric units are pascals, or 1,000 times that is a kilopascal, or 1,000 times that is a megapascal, etc. All right, strain. It's kind of, the units are kind of funny. So it's change in length divided by original length. The units for change in length are going to be inches, or it could be meters. And the units for original length are also going to be inches, or could be meters. And so the units for strain are kind of funny. They're inches per inch, or meters per meter. And sometimes you'll just convert that into a percentage. You'll see that sometimes, but usually it's more often going to be in inches per inch or meters per meter. Could be centimeters per centimeter, something like that. Here is a stress strain curve, and you are going to see a lot of these in this class. We talked about how to calculate stress. We talked about how to calculate strain. And when we do this testing on the UTM, you're going to get a big, long data set in an Excel spreadsheet as a result of your test. And it's going to provide you with the amount of force and the amount of stretch. And you're going to convert those numbers into stress and strain. And then you're going to plot them. And this is approximately what it's going to look like. To me, this looks like it's probably some type of metal. I've just looked at enough stress strain curves that I can tell you this is probably, probably some type of steel. This particular stress strain curve. But you'll get good at that. You'll see a lot of stress strain curves for plastic materials and wood materials and metal materials. We'll talk a lot more about this later, so I don't want to go any deeper into stress strain curves right this instant. Here is another stress strain curve. So this right here up to here and then going down and coming across, this is a stress strain curve. And again, we're going to talk more about this in about a month. But what we're going to say is that the slope of this linear region, there's always going to be a linear region of the stress strain curve. And that linear region right here, or going back a slide, right here, this linear region right here, the slope of that linear region is called the elastic modulus, or the modulus of elasticity, or the Young's modulus. They're all the same thing. And that is a measure of rigidity or stiffness of the material. And again, we'll talk a lot more about that later. Here are a bunch of different stress strain curves. If you see a bunch of these, you'll get pretty good at identifying what these materials might represent. So here's just some different ones where A, you can see down here, A is steel, B is copper, C is polycarbonate, D is polymethyl methacrylate. I think that's acrylic. And E is polyethylene, and F is rubber. G is low density polyethylene, and H is PVC. So just demonstrating that different materials have very different stress strain curves. Okay, this is another really important concept that I'm going to introduce now, and we're going to talk about throughout the entire semester. These terms are applicable to all of mechanical testing of materials. All right, so here's my, what example should I use this? Maybe I'll use, I could probably use a paper clip. That'd be better. All right, so here is my paper clip. I think you can see it. Okay, hold it. Okay, like that. All right, so I'm gonna try and make it so you can see it. All right, so if I apply a little bit of force to this, but not very much, if I apply just a little bit of force to this, I can apply some force and I can make it move. I don't know if you can see that or not, but I can make the paperclip move, and then when I release it, it comes back to where it was. All right, so I'm making it deflect. It's deflecting, and then when I release the force, it comes back to its original position. I think that's pretty visible, actually. You can deflect it, and then it comes back to its original position. So what that is called is elastic deformation. Elastic is otherwise known as temporary deformation. This is also like when I go home at the end of the day, the first thing I usually do is change out of my pants that have a belt on them, which is not very elastic, and change into a pair of shorts or something that has the elastic waist, because they're a lot more comfortable. And elastic means that it can stretch, obviously, and then it can come back to its original starting position or shape, right? So that's elastic deformation. It's temporary deformation. And when you release the load, it comes back to what it originally was. Plastic, okay, now I'm going to go ahead and do plastic. Plastic deformation is if I apply a little bit of force, it comes back. But if I continue past elastic deformation, I continue to bend it, you got to hold it more tightly. If I continue to bend it, all right, now it's not going to come back. Okay, so now I have deformed this plastically. We call this plastic deformation. So you always get elastic deformation first, but if you keep going, there is a certain point, and we'll talk more about what that point is. There's a certain point beyond which you're going to start to get plastic deformation. And when you have plastic deformation, that is permanent. You are not going to recover that plastic deformation. It's not going to go back to the shape that it started. What is kind of interesting, that may not be obvious, is when it was hard to see here. I was watching, but it wasn't real obvious. When I deformed this and I got plastic deformation, then when I release that, you actually do get the elastic part of the deformation back. It does spring back a little bit, not very much. Only the amount, the portion of the deformation that was elastic springs back a little bit. But all of the plastic deformation, you don't get back. It stays in that position. So if you've got plastic deformation, you already had some elastic deformation. And when you release the load, you're going to get the elastic deformation back. It's going to spring back a little bit, but it's not going to spring back all the way because you deformed it plastically. Compressive tests are basically the exact opposite of tension tests or tensile tests. So we'll talk a lot more about that later, but it's just tensile tests in reverse. Flexure testing is pretty fun. I really enjoy this part. It's one of the last things that we do in the class. And basically, this is called a 3-point bending test. There are different kinds, but this is a 3-point bending test. 2 supports, 1 on each side, and 1 in the middle. And this is almost exactly what we're going to do in Lab 8, where you are going to design and build your own beam. It needs to be more complicated than this. You can't just cut a, what is it, 2x2 or something, or cut a 2x4 to the right size and call that your beam. I'm going to give you some restrictions on what you can and can't do in Lab 8, but we're going to do a 3-point bending test in Lab 8. And basically, we're just making calculations and guesses and then experimentally determining how much deformation or deflection we're going to get with a given applied load. And we'll do some calculations, like I said, so you'll see something like this much later in the semester around Lab 8. It's not as bad as what it looks like. Don't worry, it's not that bad. And this is actually, I'm actually not going in order. This is Lab 7, is impact testing. So we're going to have kind of small pieces of metal that are about 3/8 by 3/8 by about 3 inches. And what we're going to do is we're going to put them in the impact tester in Turner 169. And what happens is you put the specimen, I don't have one right next to me right now, but you put the specimen at the bottom of the machine, and it has a big pendulum. And the pendulum weighs about 80 or 90 pounds. And you raise it up off the floor to about maybe chest level or so. And then you release the pendulum, it swings down, and then it breaks apart. And in the process, we're going to measure, we'll talk about how later, but we're going to measure how much energy the part absorbs to break, how much energy it took to break the part. And that is called impact toughness. And the reason we're going to do this in Lab 7 is because that's a good way of measuring the effect of heat treatment and also the effect that the temperature of the part has on the results. I'm still hoping to do this semester. What I often do is for this lab, Lab 7, I go and get a bucket of liquid nitrogen from the chemistry department over there in the science lab building. They're really cool. They don't make me pay for it or anything. They just, I just let them know when I'm taking some liquid nitrogen, and they say, all right, cool. So it's really fun to play around with liquid nitrogen. So oftentimes what I do is I'll say, if you want to put something else in the liquid nitrogen, like an apple core, I eat an apple pretty much every day for lunch. So an apple core, if you want to bring, marshmallows are really good because you can freeze the marshmallow and then you can eat it and you can like breathe out a vapor cloud. It's pretty cool. Or whatever you can. I don't really care. It's fun. It's science. All right, it's science. So we can do whatever, almost whatever we want in the name of science and experimentation. So if you want to bring something cool and see what happens when you get it down to negative 200 and I don't remember, negative 270 degrees Fahrenheit, we can do it. All right, it'll be fun. All right, this is impact testing. This is what I was telling you about with the pendulum. Starts up here, you put the specimen down at the bottom, it swings down, it breaks it. This is what the specimen looks like, by the way. It breaks it, and you measure the absorbed energy, and that's the impact toughness. Okay, the next two things are no, we're not there yet. This is heat treatment of steel. I'm not going to talk much about this. This is called a time temperature transformation graph. It tells you, it's kind of like a recipe for what you should do to achieve different kinds of steel heat treatment, but that's all I need to say right now. We'll talk more about it later. Shear stress is Lab 9. So this is like a sliding force. So I'm trying to break the part by causing part of the specimen to slide against other parts of the specimen. That's shear stress and shear force. Okay, now the next ones we're going to talk about are ones that we aren't actually going to do labs on in TEC 293, but they're still important enough that I want to mention them at least once in the semester. So most of the tests that we're going to do in 293 are what we would consider short-term tests. And short-term tests we can do on the order of seconds to minutes. None of these tests are going to take longer than a couple of minutes. I do have some kind of extreme examples. This one, a couple of these probably took a couple of minutes because it's stretching it apart pretty slowly. But even this is probably on the order of a couple of minutes to make it stretch apart. So none of the tests are really much longer than that because we don't have time to get through everything in 293. But there are other tests that are important mechanical properties that we just don't have time to get to. Two of them are creep and fatigue. So I want to talk just briefly about each of those. Creep is what happens to ductile materials when you apply a load over time, over a long time. So if I was to suspend this specimen that has a face on it for some reason, who knows? Who knows why? If I was to suspend it and then I were to hang a load from it, it might not deform immediately, but over time, it's ductile, and the molecules inside here will slide past each other, and it will deform gradually over time. That's called creep, and it happens with essentially all ductile materials to one extent or another. Here's a plot for creep. It's difficult to interpret this plot, and I don't expect you to interpret creep plots. Basically, the different black curves represent different periods of time. 1 hour, 2 hours, 3 hours, 4 hours. So you get different results by stretching it or applying a load over different periods of time. Okay, I won't ask you to interpret a creep plot. Fatigue is important. It's just, once again, it's that kind of a long-term test where you're talking usually thousands to hundreds of thousands to millions of cycles to really test fatigue. So the general example of fatigue is actually, it's perfect because I have a paperclip here. And this is almost always the example of fatigue that is given. I have bent this paperclip a little bit, but it hasn't broken, right? It hasn't broken. So I could even take this and I could bend it back the other way. And I've bent it the other way, but it still isn't broken, right? But I'm sure that you've had some type of experience with this where you probably know that if I continue to bend this back and forth, it probably won't take too many times. I'll count them. I just bent it 1, 2, 3, 4 times. I've bent it 4 times so far. 5. It's getting weaker. 6, 7. Oh, it went 7 times. It broke before I could bend it back 8 times. So you can bend a paperclip kind of to an extreme value like I did, only 7 times before it breaks. Interestingly, you can deform a paperclip just a tiny bit. If I were to take a paperclip, just deforming it enough to clip a few pages of paper together, you can do that virtually infinite numbers of times. But if you plastically deform it, there's only a certain number of times you can plastically deform something, most things, before it's going to fail. That's called fatigue. It's called fatigue failure. And it's really important, extremely important, for any part that is going to be loaded repeatedly or cyclically. So in your car, there's lots of things like this in your car. Lots of components in your engine and your drivetrain, your transmission, your axles, all those things are repeatedly, cyclically loaded every time they spin around or the piston moves up and down. So fatigue properties, fatigue strength is really important for lots of mechanical things that are going to be moving repeatedly in repeated movements. All right, and you can have fatigue. It's not only not only in bending, like I was giving the example, it can also occur in tension. So if I just apply a force and then let go, and then apply a tension force and then let go, and then apply and let go. If I did that enough, I could cause tensile fatigue failure on a part. Or compression, same thing, or torsion. That means twisting it like this. So if I do that enough, I can cause fatigue failure eventually if I do that. All right, and the way that we plot this is in something called an S-in curve, where S stands for stress in this example, and in, capital N, is the number of cycles, number of times you can do this before it fails. So you can use this in two really important ways. One way you could do this is by saying, all right, I've got this part in my engine, and I've designed it such that I know it's going to have a stress of, I don't know, let's use an example from this chart. Let's say that, okay, this is for plastics, but let's just pretend for a minute that this is applicable to a part in my engine, and I'm going to apply a stress of 5,000 psi. This part in my engine is subjected to 5,000 psi of stress every rotation of the crankshaft. Okay, so if I'm making it out of this material, which happens to be polypropylene, so probably not a good idea, but let's just pretend for an instant. All right, 5,000 psi. If I made that part out of this material, then I can drop a line down here, and this is how many cycles I would expect to get before it fails, like that paperclip failed. So 10 to the fourth is 10,000. 10 to the fifth is 100,000. So something a little bit more than 10,000 cycles is what I would expect to get. 10,000 rotations of the crankshaft is not very many. You know, you probably need millions or tens of millions maybe of rotations of the crankshaft if you want your car to last 100, 200,000 miles. That's one way of using this curve. Another way, probably a better way, of using this curve is to say, all right, I know how many rotations of the crankshaft I am going to get per mile, or I can estimate. And so therefore, I want my car to be designed to last 200,000 miles. And so I can estimate that to make it last 200,000 miles, my crankshaft is going to have to rotate. You know, we can do the calculation. It's going to have to rotate 5 million times or something like that. I don't know. So then you have your in. All right. The point is you have your in based on the design lifetime, and then you can do that in reverse. So you can say, all right, I need it to last, let's say, this many cycles. So now you know that the maximum stress you can subject that part to is this right here, and draw a line over this way. And now you know the maximum stress you can subject that part to. So if you need to reduce the stress, then you either need to reduce the force that you're applying. Think about this equation. If you need to reduce the stress, then you either need to reduce the, this is hard to do backwards, reduce the force that you're applying, or increase the area, the cross-sectional area of the part. Either way, you will reduce your stress. Okay, that's fatigue. That's the extent of what I want you to know about fatigue. So quick recap. We're going to talk about hardness testing in more detail. We're also going to talk about tensile testing in this class and compressive testing. We're going to talk about heat treatment and impact testing, which is the Sharpie V-notch test. And then we're going to talk about flexure testing. And then lastly, in Lab 9, we're going to talk about shear testing. All right, that's going to wrap things up for the overview of materials testing. In the second video, we're going to talk about the instructions for Lab 1 so that Lab 1 goes a little bit more smoothly and you know what we're going to be doing next Tuesday when we actually do Lab 1. So that's going to be it for this video, and I'll see you in the next video.